Oh, excuse me. Yeah. Another draft physics video presentation. Obviously, no production values today. Already made this video. Computer crash thing. Just very depressing. So do it again. Don't wanna. So anyway, there is a chat from yesterday, a conversation with Zohar Kohevi, and the give and take exchange explanation, and everybody is different, and everybody can understand different things, and they don't understand other things, and so it's probably good to have those kind of conversations to get to people's hanging points and whatnot. So it may be of value to you or it may not be in terms of how well you understand already some of the points I've made. So anyway, link below to that. And there was a comment that I have hence deleted in the previous unrecorded video. So regarding this, it was a Ken Wheeler, just a link to a video. It doesn't really say anything, but it's sort of this argument that magnets have different properties or something. Comparing giant magnet to giant magnet, and clearly the difference is in the size of the magnet. I mean, in the shape of it. So if you have the same strength magnet, they're both N45s. Obviously, you can shape them differently, and their field will be different. So that shouldn't surprise anybody. But that's not the argument Ken Wheeler's making. Ken Wheeler's making an argument that somehow it's not about the shape of the magnet. It's something about the fact that the larger magnet has less capacitance or something, and the smaller magnets have higher capacitance or some kind of nonsense. And it's nonsense. But to get to the point of the fact that magnets tend to express a greater magnetic strength, let's say, at certain positions in the magnet. Consistent with my filter idea, that if you think of the magnet as a filter, the filter is basically saying, all this yellow stuff just reflects off the one end, and anything not yellow ends up coming out the blue end. Okay, goes through the yellow and comes out the blue end. So at the blue end, you have all the blue reflections plus all the blue that went into the yellow. So everything comes out blue, and then everything comes out yellow at the other end by the same principle, that the yellow transmits through the blue and ends up coming out the yellow. Dot, 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 dot. It's kind of a simple diagram of the basic function, which creates these two polar opposites, one end repulsive to protons, the other end repulsive to electrons, blah, blah, blah. Blah, 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 blah. This lighting issue is really annoying. So anyway, so what you can notice is that if it was a filter and you said, well, the more material it has to go through, the more likely it is to be obedient to the filter, you could sort of understand that the longest distance is this distance. So it's the most filtered at these corners, you could argue. These ends would have the most going through the magnet. Something coming through would go through the most magnet at that angle. So obviously there should be a slightly increased amount of purity of blueness and a purity of yellowness at those corners. And that shouldn't be a huge surprise. Likewise, this is very long, this distance, and this is very short, this distance. And so obviously the polar magnetism is stronger, at the pole, okay, at the poles. And but yes, if you had another magnet right next to this one of opposite configuration, you could sort of understand that the opposite effects would happen, and these two would react as individual charges, and these two would act as individual charges and be attracted, and blah, 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 blah. So, so the video doesn't demonstrate anything that isn't already known. So it's called mapping Monster magnetic field. And it really doesn't do that. But there's no demonstration of any violation of Maxwell's laws, in the sense of the fact that this obeys, magnets obey the r squared and r cubed rules depending on their configuration. And you can't make an argument that you have a more powerful magnet that has a field that doesn't go as far. How far the field goes is going to be dictated not just by the shape of the magnet. So if you have a very tall magnet, obviously it's going to have a stronger field in these end directions than it's going to have overall this distance. But I shouldn't have to explain the obvious. But it tends to work out that way, that you kind of have to. Alright, so I think that disposes of that fundamentally enough. Get to this guy later. What we want is this guy, Biezen. It looks like the beginning. Hopefully there won't be ads. So is there something? So there's a lot to preface this argument with. This whole idea of scatter and the transmission of light. So maybe I'll do a little bit. There's simple process, but obviously the subtlety of the mechanics is sort of important, and they don't have any of those details, none of them. So the simplest idea is that you have a substance, even the atmosphere, okay, the air, and it's full of something that can convey pressure in some way. So in a sense, you hit it with a pressure. Now, whether you think that's some silly wave, or whether you understand that now that's clumps of energy, you're hitting one side of the drum essentially, and the expectation is the other side of the drum will, after some little time delay, convey the same action. So if you dent this side, the dent, so to speak, of you hitting it will travel through the material and dent the other side in a similar fashion that will in some way release the motion that came in. So you're trying to keep a coherency between these two things, what goes in and what comes out. Stupid lighting. Such an issue. So that in principle is what you're looking to find. Now the trick is that this wave is gigantic, thousands of atoms. The wave covers thousands of atoms. Even blue light is covering thousands of atoms in terms of this polarization length. Height is coming into thousands of atoms, and so it doesn't make much sense that this giant wave somehow interacts with one electron on one of those thousands of atoms. So you have 1,000 atoms, you have one electron, and you're going to say this entire wave is somehow going to interact with this one little tiny electron, create it, and then create on the opposite surface the electron to do an action that's going to be the same kind of action that happened here, that's going to release what came in. So somehow you're going to get what went in comes back out somehow. And they have no explanation for any of this. How's this giant thing covering this huge area create that effect? And so scatter comes in the sense that somewhere this breaks down. Okay, it doesn't get through this process because of some difference. Somehow this isn't coherent, and it ends up going this way, or it ends up going some other way, and the energy ends up going in ways it's not supposed to go, and you end up with your frequency going out that way, or you end up with something called heat or something else, or motion. In some way the whole thing is absorbed as movement of the whole object, or it's and that essentially is what heat is. Heat's evidence of motion. And when you have heat trapped in a circle, then you've created a perpetual engine in a sense, because the heat will just keep traveling in a circle and traveling in a circle and traveling in a circle and traveling in a circle, and you can get the idea that ends up being motion. And the same idea is going back and forth in the sense that you go forward, cause motion. All right, go backwards, stop the motion, go forward, cause motion, blah, 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 blah. All right, I've been over those subjects a little bit before in the past. So, the what I would argue has to take place for there to be successful transmission is you can't absorb the energy, because then you can't transmit it, because if you're using it to do motion. So you can't get it caught up in a heat cycle. You can't get it trapped as a motion engine. The energy has to be released. So I would argue that what's taking place is all these atoms in the atmosphere and everywhere else, they're all in places that are semi-comfortable. All right, they can have motion, they can swirl, they can be doing certain different things relative to each other. But I mean, their connection to their environment, that is, the stuff around them, stays relatively consistent, or wishes to. They're under an equal pressure between each other. The electrons. So whether it's electrons connected to atoms, like this is a nucleus and there's a nucleus over here, and somehow these are connected, there's a pressure between the electrons that's maintained, and there's pressure between the other electrons in the atom and all the whole thing. So there's tension between the molecules, and it's the tension that you want to transmit this action through. And so the idea is you have a motion in this direction. I would argue the quanta of the photon. Okay, the photon's made of bits at a frequency. Okay, and the bits are going to hit something, cause it to move. It's going to move into something else. Blah 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 blah. So if you understand that there's the same little bit that's here is also bouncing back and forth between the electrons, maintaining their hatred of each other. And what you're doing is basically going to hit this electron. You're going to move it a little bit, and it's going to convey, because of its motion, it's now going to compress the space that these little bits are moving in, and that's going to put more pressure on this electron, and this electron is going to start moving in that direction. Now, the trick is, okay, is for this not to be absorbed as motion, this has to go back to its original position, or else the whole object moves, and you've used up the energy of this motion, creating motion in the atoms. Right? The whole big giant atoms start moving. But you don't want that to happen if you want to transmit the energy. If you want to transmit it, you can't be causing motion and transmission. So that's not going to work. You'll have some, just because there's a bit of time used up here. In terms of you're taking some of the time off of this motion, and that this photon won't travel the same speed. It won't get to point B at the same time it would have gotten to point B. That is the other side of the surface. So there's one surface, here's the other surface. It's going to be in here for more time. Okay. So it's not going to get to point B in the same time. So there's a little bit of motion. So a little bit of its reality is used up in the sense that there's a delay, and that delay means that energy had to go somewhere. The energy gets here eventually, but it's getting here slower. So that means that you have to account for that in terms of a little bit of motion cost. But anyway, I don't want to get into all that. So the idea would be is that for this to work, this is what has to happen. You hit this. This transfers the energy to something else, the next electron, and then the next electron transfers the energy. And what I would argue that happens on the surface is the electron goes out so this is the exterior surface, and then on the energy that takes to go back in, on that absorption, that's when it releases the photon again. So the energy is released when it pushes the surface out, and the surface moves back this way. And when it moves back that way is when it gives back the photon. The extra bit being reflected back to the universe. So a bit that would have gone into the material ends up going back to the universe. And that's going to be this recorded here. And if this keeps happening through this process, this nice straight line process, everything's fine. The trick is that if the frequency is too high, then you can sort of understand that the bit hits this bit, moves it, the pressure moves this bit, and it's moving, and then this bit gets hit again before, okay, it's had its position relaxed, and now this one's moving away, so it's already moving. It's not going to be able to transfer the energy efficiently, and it's also now not going to be able to go back to where it was because this extra pressure is pushing it, and now it's going to tend to move in other directions because it's moving further away from its proton first. I mean, it's connected to a proton here, right? So you could sort of understand that if it moves a little bit, that's not a big deal. But if it moves a lot, okay, now it's going to have to move in this direction because the attraction to the proton is now going to pull it in a new direction. And so now its motion is going to be way off. And now when it tries to go back, it's going to be releasing energy in the wrong direction, a new direction. So high frequencies end up pushing things that are already moving. Low frequencies allow the system to relax before the new hit. It allows the system to at least stop. So the motion is basically, I sort of pointed out how this engine would work, but I mean it's motion, then it stops, then it moves, then it stops, then it moves, then it stops, then it moves. And the point is you need to let it stop, okay, before you hit it. And if you hit it while it's still moving, that's when everything goes wrong. So blue light, having a shorter frequency, ends up in the atmosphere hitting electrons often that are already moving, and that really kills the process, ends up turning the motion, redirecting the motion or turning the motion into heat. And heat is the same thing as moving the atoms, or velocity or acceleration. Alright, so another interesting feature. So anyway, I don't have all this perfectly, I mean, I can't give you the perfect diagram yet because I'm still in process of thinking about it, but another feature to understand is polarization of the light is pretty much consistent with the frequency of the light. So the light is as thick, okay, as it is the frequency is long. So those two distances are proportional. And if you think about the fact that the polarization means it can be polarized in any one of these dimensions, directions, that's essentially a circle that the light hits on. It can be polarized this way, or it could be polarized this way. Each photon can have a different polarization. And so the trick is that as I increase the polarization, the area the light's going to fall on is 4 times bigger. So as I double the frequency, I quadruple, okay, the amount of area that those photons will fall on. So if you understood that the real substance of the photon is just the little bits, the quanta, at a frequency, I could say if I was to hit it with 10 little bits in this area, you can understand that I'm probably going to have a much higher likelihood of hitting electrons where the electron in front of the electron I'm hitting is already moving. This electron's already moving, so I can't move into that pressure. I can't push him, theoretically, because he's already moving in the same direction I am. So it's hard to push something that's moving the same direction you are. And you can understand that if I take those 10 things and put them in this big area, right, that there's a lot less likelihood I'm going to be hitting anywhere near the same spot. And so I'm not going to tend to do this thing where I hit something that's already moving. I'm less likely, 4 times less likely to hit a thing that's moving, the higher the frequency. So that's why the big waves, the long wavelengths get through, the low frequencies get through, is because they're less likely to do this thing where they push on something that's already moving. And they're more likely to, the shorter the frequency, the higher the frequency, the less space the energy is falling on. And therefore the more likely you are to push something that's already been pushed. Alright, so that's another point to make. And then there's still another interesting aspect to all this. So it's probably best for me to do this ahead of time, then I can reference it in his video, and point out where, see, there nothing explanation, I have a something for an explanation. Now another interesting feature of scatter with the blue light. So the blue light scatters out easier because it's more likely to do this double push thing. And the trick is when it scatters, it's likely to go perpendicular to the direction it was traveling. And this light that comes out perpendicularly is likely to have the same polarization. So its plane of polarization is going to be all the same. So it loses having any mixture. By going through this process, it comes out as only one polarization. All the photons have the same polarization. So a way of thinking about how that's taking place, I'm not saying this is absolutely complete or correct. Got my chalk. Now what do I do? I see it. Well, I have to get a new, well, I have another little piece of white here. I get another piece of white chalk. Oh, so much technical bullshit to go through here. Alright, so something with an interesting way of looking at this. So I was thinking about scatter, and I was thinking you could have a bunch of particles that you're going to be hitting with photons coming down. And the photons, like I said, have a thickness to their wave, okay, the polarization. You can almost see that. And they have a frequency. So they're all at the same place. And they're all rows at the same place, little soldiers lined up, so to speak. And so if they hit something, and they did go perpendicular, like a proton diverts the force, perpendicularly, like the magnet, right-hand rule kind of thing. You could sort of understand that, all right, so let's say these little balls all hit a surface at the same level of the material. You could sort of understand that if I redraw that, so and they went right, instead of going through, they turned right, and each one of them did it. That what I've essentially done is taken the polarization and converted that into a frequency, because now they're all at the same distance apart based on the polarization. They're all moving in this direction, and in a sense I've converted the distance, you could even say the distance between the atoms in the atmosphere, so the distance between the different atoms, how much distance there is between them, could sort of be illustrated this way, in the sense that if you hit an atom here and then the next atom is almost the same distance, they're all almost equidistant from each other, that whatever that distance is, that would essentially create the new frequency. So the frequency would end up being proportional to the distance between the atoms, because they're all getting hit and they're all sending it the same direction. So in a sense you have a polarization to frequency converter, and because there's a consistency between the polarization of something like blue light to the distance of the atoms, it turns out that's a lot more likely to survive the process of this conversion, of this turn it makes. And that wider wavelength light or larger polarization light wouldn't survive it, because there wouldn't be any, they could be any kind of distance apart based on what atoms they happen to hit. It would be much further apart, and it could be variable. So their frequency could end up being varied, where the frequency of blue light, if it's the same as this distance, would end up being selected out. Yeah, so I think it's just an interesting fact that you can convert the width of a ray, okay, into the frequency of a ray, right? Frequency, just by doing that right turn, because now the distances are further. This one starts from here. This one starts from here. This one starts from here. So they have a different starting line going in the same direction, which ends up just being a frequency. So, just saying, interesting fact. Maybe quite relevant. Where's clean that up. Alright, so on to the video and such. Or maybe I'll take a break. What the hell? I can do it. My prerogative. Alright, let's try to finish up here.
Welcome to that lecture online, and now we're going to take a look at what we call Rayleigh scattering. Again, we're trying to figure out what a photon is. And a photon, part of sunlight, as it enters the Earth's atmosphere, tends to scatter in the Earth's atmosphere. Now, why does it scatter? Well, there's different phenomena, different reasons why it scatters. One of them is what we call the Rayleigh scattering. And Rayleigh scattering is where sunlight, where we have relatively large photons, scatters over very small little particles called the nitrogen and the oxygen molecules in the air. Now, in relationship,
right, it'll scatter off anything in the air. So it'll scatter off carbon dioxide or carbon or some other crap, dust. It'll scatter off a lot of stuff. But the point is that the stuff that makes it scatter in this particular way, where the high frequency light scatters 9 times more than the low frequency light, is why it's Rayleigh scattering. So it has to do with the fact that the transmission molecules, the atoms that are transparent substances, nitrogen and oxygen, aren't transmitting. They end up deflecting. And I would argue the reason why they deflect, it just has to do with the fact that the frequency is higher than the distance between the electrons, both associated with to each other in the atoms and associated with each other as separate molecules. That distance means that there's a certain lag time between how long it takes for the movement of one electron to be conveyed to another, and that you're moving something faster than the change you made in the previous electron hasn't finished yet. You haven't finished pushing your neighbor. You're pushing the guy in front. Somebody pushes you from behind. You're pushing the guy in front of you. And each one of us, to do the pushing thing, our hands aren't already on each other's back. So it's not going to be a instantaneous flow of push. Each one of us has to push. So it takes time for us to do that. And if I have somebody pushing me faster than I can move my hand back and forward, you could understand that's going to make a mess out of the whole pushing theme, because the guy in front of me is not going to be there for me to push on.
Size-wise, imagine that sunlight has a wavelength of 500 nanometers on average. So the lambda of sunlight is about 500 nanometers, and the typical length of a nitrogen or oxygen molecule is about 300 picometers, which means the wavelength of visible light is more than 1,000 times the size of the particles that it scatters on.
So he didn't really point out that the 500 nanometers means it has a polarization, a wave height of 500 nanometers also. So the waves are 500 nanometers apart, but they're also 500 nanometers from top to bottom, this way. Okay, and somehow that giant thing that's 1,000 atoms large, and it's still going to interact with one electron. Or even the very idea that it's wobbling a single atom is kind of silly, just because we don't have an explanation with this vibrating atom. Why would the atom vibrate? How does it vibrate? We can understand how a pendulum swings, right? I mean, you got to go against the force of gravity and against, so the pendulum really gains speed, and then it slows down, and then it stops, and then it accelerates and gains speed to go back up to the other side. There's a real physical mechanism to the wobble, so to speak. There's no explanation for any of this wobble. How does something that big, thousands of atoms across, affect a single electron and cause some sort of atom or a single atom to wobble? Why wouldn't it wobble all the atoms? And then you have an energy dispersion problem, because then you have no way of dissecting that photon's energy and spreading it over a whole bunch of atoms.
You say, well, wait a minute, how can it do that? There's this huge wavelength, this huge electromagnetic wavelength of, when you take the wavelength of these huge photons in comparison to the tiny little particles, how can scattering actually happen? Is there a collision taking place? And how can this big photon find that tiny little particle to scatter on? Well, it's because scattering doesn't happen because there's actual collisions.
So he just says that, right? He doesn't have any evidence or proof or way of proving that. He's just making up a story now. So they have this huge gap that he just pointed out, this gap. He's saying here's something that's spreading over thousands of atoms, and yet I have to come up with some reason why it selects this particular atom and this one it wobbles. It doesn't wobble all of them. It just wobbles 1 in 2,000 atoms right here for some reason. This thing spreading over all these atoms somehow just wobbles this one atom. And yeah, there's no rational description of why that happens.
It happens because there's some electromagnetic interaction between the photons coming in and the particles. So let's...
No, the interaction is the photon is a force. Okay, it is the same force that's electromagnetism. It is the force. It is the field. It's the actor. It's not some player. It's not the thing being acted on. It's the thing that acts on.
Take a closer look. Here's a nitrogen molecule. Nitrogen has 5 valence electrons in the outer orbital, in the outer energy level, I should say. And so we have two nuclei that are positively charged and 10 electrons.
So it's just, I don't like mixing the two subjects, but this is sort of a chemistry. It's sort of getting into the structure, and that's a really interesting subject, but it does complexify things. So what he's basically pointing out is that, like hydrogen, nitrogen doesn't naturally like to be in single atom form. That is, it doesn't like to have a nucleus, with protons and then the electron. It doesn't like to be in that single atom form. It likes to be in a combined atom form, where the two nucleuses are, and they share, okay, I think he said 6 electrons. So they have 6 they share, and then 3 each or whatever that they don't share. So they're both using these electrons, okay, and they're both not sharing these end electrons. But that's sort of not important. That just shows how strong the bond is. But you can do the same thing with say a hydrogen atom, and understanding that is really important. Understanding the tension between all of this stuff. But the thing you really need to understand is that the atoms are always protons in the middle, and electrons on the outside. And so whatever pressure there is between these electrons is likely to be the same pressure there is between the different atoms themselves. That the electrons are trying to find peace, and they have to find peace not only with their own environment, that is the repulsion to the other electrons and their attraction to protons, but to the field that they exist in is also going to define how comfortable they are in a position. All right, so I want to do hydrogen real quickly. So the interesting fact is that this is sort of a polar argument, that if you took the idea of a basic hydrogen atom, I guess 2 colors would be appropriate. You have the proton and the electron, right? You can see that almost well enough. Now that's really polar, right? I mean, it's obviously, looking at it from this side's really negative, and obviously this other side is really positive. So this is a really reactive, potentially reactive atom when it's by itself. But you could understand that if all I have to do, okay, to make it a lot less reactive, is I put another proton here, and I put another electron here. And pretty much now I have what you could say, in a sense, is almost a standard atom. Would be 1 neutron, which would be this part, then an electron and a proton. So in a sense it's hydrogen, because you have 1 neutron, 1 proton, 1 electron. So it's consistent with the rest of the periodic table in that sense, that there tends to be a relationship between the number of protons and the number of electrons. But you can also, like I said, just as I just pointed out, you can see now it's a lot less polar in some respects. It's still very positive this way and positive this way and negative this way and negative that way. But structurally, it's not as lopsided. It's more evenly distributed, and from a distance, it's going to look like it's neutral. It's going to have as much electron as proton from most positions. See, because even when you're looking at it this way, you're seeing both the electrons. So, it balances. And likewise, when you're looking at it this way and seeing the electron, well, you're also seeing both the protons. So it's a lot more balanced. And all it is just the two atoms stuck opposite ends. So I'm just saying this is where the chemistry part is going to get even more interesting when I finally can get to that part. But anyway, continuing.
In total, 6 of them which must be shared in a valence, in a sharing relationship, and then we have 2 additional electrons which can be in the outer orbitals of the individual atoms, forming a molecule like that.
All right, so as I would argue that the whole orbital thing makes the whole thing make even less sense. So he's saying some gigantic wave, thousands of atoms across, is going to have an interaction with some electron that's moving around in valences. I don't see any practical way that's going to happen. So anyway, so clearly I would disagree that the standard model, the Bohr idea of things orbiting, just breaks the whole idea of what really atoms are. And what atoms are is charge, and what charge is magnetism, and they're really just magnets held in tension. Monopoles of magnetism held in tension. They're attracted to one thing, repelled by another thing, and therefore they have a balance of their will to move.
It turns out that this molecule is symmetric in all respects, so that the charges are symmetrically divided over, so there's no one side that's more positive and the other side that's more negatively charged, so there's an equal charge distribution in the molecules, perfectly symmetric.
All right, so I would argue that that's only an appearance from a distance. So it's like a neutron, I would argue, is polar. It's a dipole. It has a charge in the sense that it's from one side it's going to look very negative, from one side very positive. But from a distance, that's going to blur into nothing, an equal amount of both. That's what happens with magnets from a distance, is they turn into nothing. That's why they obey the R-cubed rule in terms of their field strength, is because it all turns into purple. So if one side's producing red and one side's producing blue, the further away you get, the more mixture you see. You see less of the stuff that was pure blue, and you end up seeing more of the stuff that's purple, where both are mixing. And the further you go away, the more it looks like purple instead of blue and red. So if I did the same thing with light bulbs, I put a red light bulb and a blue light bulb right next to each other, when you're up close, you're going to see it. And especially if you're looking at it from the red end or looking at it from the blue end, it's going to look really polar. But if you move away from it any distance, the light's going to look purple. I mean, it's what fools you on TV screens is merely your proximity. The fact that you can't see the pixels. The TV's fooling you, okay, by distance.
Same with oxygen, except with oxygen we have 4 valence electrons here and only 4 being shared between the two. But the principle is the same, and so it turns out that these molecules...
It turns out, he says, it turns out. They don't have any evidence for this turns out theory. They don't have any explanation for it. They're just making this up, essentially, trying to contrive some reason why there's some mechanism. So they're going to try to say, well, if you hit the neutron this way, this happens, and if you hit it on its side, something else happens. But they have no explanation for how the atmosphere would have neutrons in any kind of consistent orientation. They'd almost have to argue that the magnetic field is somehow orienting all the neutrons in the atmosphere and therefore causing the scatter. But then you could make the argument that, I can take it out of the magnetic field in the sense I can create an experiment where I have a neutral field and the same effect is going to happen. So anyway, they're just trying to contrive an explanation.
Can actually vibrate in various directions. So the molecule can vibrate like this, it can vibrate like this, but it's more likely to vibrate like this.
Right, and there's absolutely no mechanism for it to absorb something that's huge. So something is traveling over a gigantic amount of space from its tiny size. This giant thing is somehow going to make it alone vibrate. Not its neighbor, not the guy next to it, not the guy next to it, just it. It's going to vibrate in some way for some reason. But they don't have any explanation for why it would move this way and then why it would stop and then move this way and why it would stop and then move this way. They don't explain any mechanics for this vibration.
And so an electromagnetic wave or a photon comes along, and of course a photon, what does it do? It changes the electromagnetic field around these air particles, the air molecules for example, and it causes them to vibrate at the same frequency as the vibration of the...
So somehow the thing vibrating the field somehow gets consumed and it stops vibrating, and instead the atoms are vibrating. So somehow it conveys its vibration to the atoms without really interacting with them in any direct way, and in some bizarre manner where something huge somehow only affects one little thing and not all the rest. It makes no sense.
Electromagnetic radiation or the vibration of the photons, which means that as the photons come through and they vibrate, the change in the electromagnetic field will cause the molecules in the air to vibrate as well at the very same frequency. Now they're more likely to absorb the energy in this direction.
So there's obviously a transfer as group behavior. There's a transfer of this momentum at a frequency. So it can look like, oh yeah, that looks like a vibration, like a wave of soldiers can look like a vibration, or a wave of bullets, or a wave of cannonballs, or a wave of anything. But that's a group behavior. The real event is not a group behavior. The real event is the individual bits, and that's the part they've just totally lost sight of. All they can see is the group dynamic, and they can't do the physics because they don't have a mechanism, so they can't do the real physics.
This direction, and since the molecules have all kinds of different orientations, you will then find that the scattered light, because what happens is a molecule will absorb the energy and then re-emit the energy without any loss. It'll transmit the energy.
It'll without any loss. It can change its direction. It can make the momentum go in a new direction without any loss. But it's still the same momentum it has to release in some other direction.
In this direction more readily than in this direction, and because of that, the air tends to polarize the scattered sunlight. And so there's a certain polarization factor to it. But
there is a certain polarization factor to it explained nowhere. No explanation for how it's polarized. What mechanism polarizes it. Clear, and I think it's also kind of clear that the upper atmosphere scatters more blue light than the lower atmosphere, mostly because there's more of it up there than by the time it gets down here. But I think it does it more readily anyway. And that's further away from the magnetic field.
Because of that, because of different orientation, here I have a little picture of it, a primitive picture I may add. So you have the sunlight coming in from the sun, it enters your atmosphere, and as it starts hitting these air molecules, it begins to scatter out, but more so in one direction versus other directions, so the light tends to get polarized relative to the direction of the incoming sunlight.
So, again, he says it tends to get polarized in the direction of the incoming sunlight. But there's no, like I said, that you can tell that it's polarized, okay? As I pointed out, if a surface is going to change the direction of something, it's coming down this way, it's going to be turned this way. You can sort of see that by pushing it down this way, having a polarization, I'm also creating a frequency this way. So doing this and then moving it that way, you can just see if this was the polarization coming down, I've converted it into a frequency when I move it perpendicularly. That's the better explanation.
Because of that, and also what we find is that the amount of scattering depends on the wavelength of the incoming light. It turns out that the intensity of the scattering, the amount of light that gets scattered, is proportional to 1 over the wavelength to the 4th power. It's kind of interesting. Let's explore that for a moment. So we know that the wavelength of sunlight ranges anywhere from 400 nanometers for the purple light to about 700 nanometers for the red light. So this is for red light and this is for purple light. So which light gets scattered more? Well, it turns out that the shorter the wavelengths, the greater the scattering. The longer the wavelengths, the less the scattering. So it turns out that
So again, how long the wavelength is also telling you how big the circumference of the circle is that it's going to fall on. So the polarizations are mixed. If I mix a bunch of polarizations, you can just get the idea that that's just the same diameter in the same space. But as I make that circle bigger, as I increase that diameter, I quadruple the area that it's going to fall on, and that's the key factor. The higher the wavelength, the shorter the frequency, the quicker the frequency, the smaller the area the force falls on, and the more likely it is to not obey the rebound rules.
If there's a higher frequency photon with a shorter wavelength, it's more likely to interact with the air molecules, with the nitrogen and oxygen, more likely to distribute its energy into those molecules and get it re-radiated out, so that the light no longer comes directly towards the observer, but that it's scattered in different directions.
So let's understand, it doesn't re-radiate out as heat. So unlike in like ultraviolet light going through a piece of glass, that's converted into heat, as far as I understand. It might also be coming out the edge of the glass. I don't know. I haven't seen anybody do that experiment. But the point would be is it's not being retransmitted in a new direction. It's being converted into actual motion, okay, of the atoms as heat. And again, as I said, if you organize that motion, then you have velocity for the mass itself. I mean, it's just all falls together. It's just all fits. But anyway, so just understand, he's not saying it's lost its heat. It's not because it's moving the atoms. They don't go to some new location. If they go to some new location and stay there and then move to a new location, that means they're gaining momentum and the energy's lost. It's used up. You can't move something and then, you know, you can always give it back later, but the point is while you're using it, and so the heat would be, well, once it reaches thermal equilibrium, then it's a net zero. So I guess, yeah, you can only borrow energy. You can never destroy it. So you could re-radiate it, but you wouldn't be re-radiating it consistent in time. And so you'd have little hope of re-radiating it at the same frequency that you took out. And the frequency of most radiation is infrared, and the atmosphere would have to be really hot to be producing blue light. So to produce blue light by heat would be really unlikely. So it can't be, you can't blame heat or movement of the atoms for the transmission of the blue light. You have to just say that it's diverting the blue light. It's not converting it into atomic motion. It's doing the same thing. It's just pointing it in a different direction.
Part of the reason why the sky is blue is because blue is more likely scattered in this fashion because it has shorter wavelengths. Shorter wavelengths means higher intensity of scattering. And so therefore, the sky is blue because blue light tends to get scattered.
Right, so that's just circular. He just did a circle, right? He just says it is because of this formula. Well, yeah, the formula is the byproduct. That we know. That's the end result. Okay, so, but you didn't explain why it's more scattered. You just pointed to a formula. Well, yeah, okay, we already know the formula because we know what the outcome is. You're not explaining why that outcome was produced. I mean, it's the gaps in their understanding are huge.
Way more than red light. The reason why the sky doesn't look deep dark blue is because all of the wavelengths get scattered as well, but not quite to the same quantity. If you
No, I think that has more to do with just the intensity in terms of the dilution by all the other scattering that's happening. So this scattering is only one portion of the scatter, and therefore it can't kill. It's not the only thing you're seeing. Like clouds and other things, they're also going to transmit light, and they're going to transmit it without filtering it for the blue light out.
A little chart of that, and so you say this is blue light at 400 nanometers, or purple light at 400 nanometers, and this is red light at 700 nanometers. The amount of light getting scattered out will vary like that according to wavelength. A much greater proportion of the blue light gets scattered out, and very, very few of the...
Right, so it would be the same curve. It's another one of these things. It's almost showing you the edge of a circle, right? It's almost showing you that this is about the fact that if you double the diameter of the circle, you quadruple the you quadruple the area of the circle. So it's almost just showing it to you. Quadruple, right? quad sounds like it should be 3. Well, whatever. Fourfold. You fourfold the area.
Photons get scattered down in comparison. Ratio-wise, let's take a look for a moment. Let's say that we take 400 to the fourth power, and we take 700 to the fourth power, and then we'll take that ratio and see what we get. Actually, we don't have to do 400. We can go 4 by itself and get rid of zeros because we just want to care about the ratio. So 4 to the fourth power is 256. 7 to the fourth power, oops, that's too many. 7 to the fourth power is 2,401. So ratio-wise, how much more the blue light gets scattered out compared to the red light? If we take the 2401, because it's inversely proportional, so we have to take the inverse of that. So 2401 divided by 256, what do we get? We get 9.38, 9.38, which means that blue light is more than 9 times as likely to get scattered out in the atmosphere as red light, so ratio of about 9 to 1. Now,
and again, I would argue that really just has to do with the threshold of the pressure between the electrons, and that once you get to 300 or 400 nanometers, you're more and more likely to hit something where the other thing still hasn't stopped moving, and that's the key to misdirection.
Part of the reason why not 9 times as many blue photons get scattered out is because the distribution of light coming to the Earth doesn't have as much blue light as it has more of the yellow, green, and orange light.
So I don't think there's anything demonstrating that either. I think per number of quanta, it's the same. Obviously, the blue light's distributed over a much smaller area. It hits less surface, but it hits it with more stuff.
Anyway, so to get a feel for the Rayleigh scattering, let's take a look at the equation right here. This is the equation that defines the Rayleigh scattering. Notice the 1 over lambda to the 4th factor in there. Also notice that it depends on the number of molecules in the air, of course, and how effective those molecules are at reflecting or scattering the light. So different molecules have a different proportion in which they can...
Right, so that would be exactly proportional to the fact that different molecules will have electrons in a different amount of tension, and so movement between the electrons takes a different amount of time for them to rebound to their positions. So the more tension they're under, the quicker they rebound. The less tension, the slower they rebound. Therefore, the limit on how fast you can send a signal through them is changed. So more tension means you can get a higher frequency through them. Lower tension means it's harder to get a higher frequency through them.
Scatter the light. Also, of course, the intensity is proportional to 1 over the distance squared. As you go farther away from the source, you get less and less of the intensity. And finally, we have the scattering angle theta right here. Notice that when theta is equal to 90 degrees, cosine of theta goes to 0, you have a 1 there. If it's either 0 or 180, you get cosine of that is equal to 1, so you get 1 plus 1 equals 2, which means that the scattering in this direction is about twice as much as the scattering in this direction. And so that's, by definition, Rayleigh scattering.
And that's presuming the light's coming down from the top. So he's saying it's twice as likely it comes out the side than it does reverse or go through. Essentially, that's what he's saying, I believe.
Again, understanding a photon is understanding how it interacts with matter. Here we have a photon that has a wavelength that's over 1,000 times the size of an air molecule, yet...
Right, so he just said it again, okay, just to say 1,000. It's spreading over a surface that's at least 1,000 atoms in diameter. And if you understand that the polarization can be in all kinds of directions, that's 10,000 atoms. But anyway, a lot of atoms.
There's the interaction because of the changing electromagnetic field that causes the scattering to take place. And hopefully that again gives us another window.
I think the only rational way to understand light is that it's basically these little bits, and the rest of it's just group behavior. But the little bits are all the thing doing the interactions. They're having single interactions with electrons, and all you're really doing is saying what system takes that single interaction that happens on one end of something and conveys it to the other end consistently without bending it or distorting it or perverting it. And so the argument simply is that as the individual little bits of the photon hit, they do go straight because they do hit electrons in a straight manner. They give them momentum in the direction they're moving, and so they're conveyed straight, and they end up coming out the other end because the electron gives back what you gave it. The momentum is given back when the electrons move back to the substance. Now, if they don't move back to the substance and the substance moves, then there is no photon given back, because the movement is where the photon is still active. The energy of the photon is in the movement.
To look at what a photon actually is. A photon is a piece of energy, and as it travels through or near charged particles, the interaction is not because there's actual collisions. The interaction is because the changing electric field inside the photon causes the interaction to occur as the charged particles pick up that change and transfer the energy from the photon to the particle, and then can re-radiate that back out as the energy.
So no explanation exactly how it does that. How does the field around the photon move? How does the photon convey that movement to another object and absorb all of the wave, disappear somewhere? So the wave doesn't keep waving. The energy goes into some other electron waving, moving. Okay, but it's only one electron, and the photon itself is gigantic in terms of where its energy is distributed over is a gigantic surface. And yet this is all happening to one electron. It doesn't make any sense. Their theory is incoherent.
Then gets put back into space.
I mean, he emphatically says they don't hit, they don't interact, he has no evidence proving that isn't the right answer. It's just not the answer he's chosen to believe.
Different direction. So basically, these nitrogen and oxygen molecules become like radiating dipoles. It causes the electrons inside to vibrate according to the frequency of the photon and then re-radiate that energy back out. So they temporarily absorb and re-radiate out the energy of the photon.
Right, and through all this wavy stuff, somehow you get straight lines. No chance.
And so we have a photon coming in one direction, getting absorbed by a molecule, getting pushed out in another direction, goes on its merry way, same wavelength, different direction, and that's how photons get scattered.
Right, and that's how it happens. And there's absolutely no explanation of the mechanism. So he's just saying pendulums swing up and down, and he's really not telling you anything. He's not even explaining how the velocity has to be absorbed by the force of gravity. There's complete seats of motion. The energy is converted into this thing called this virtual placeholder called potential energy, which just means you've changed your gravitational location and now you have space to fall into. That's all it means. Your potential isn't something different. I mean, if I put something in my hand there to hold it up, I haven't changed the potential in any real sense, except it'll never be realized because it doesn't have any space to fall into. But anyway, that's a whole other argument. There's no such thing as potential energy
in the Earth's atmosphere. Pretty ingenious way of making the scattering work.
Right. It's a silly story, and that's all it is. They have really just tiny pieces of evidence. They have the byproducts of the experiment, which we all agree on, but they have a completely incoherent explanation of how the pendulum swings. They're saying some, bent space, fold space, and the pendulum swings up because the space got folded and it bent, and it's just nonsense. Okay. So enough of a video, I guess. Second try. Quit while I'm ahead, hopefully, and such. Hopefully we have a video. Probably something else I could add, but won't chance it.